So in this part of the course, we will discuss different ways of improving the scalability of coherent shared memory implementations. We will start by looking at how to make the coherence itself more scalable. When you talk about scalable systems, people typically think about three different options how to implement shared memory. Either you can have a uniform memory architecture, or UMA for short, sometimes also referred to as symmetrical multiprocessor, SMP. That's the kind of system we've been looking at so far, where we have processors and caches on one end of the system interconnected by some kind of interconnect to the memories. And the symmetric property here is that the access time from any processor to any part of that memory is uniform. So it doesn't really depend on which part of the memory a specific processor is accessing. That is not true for systems like the non-uniform memory architectures that we're going to discuss later on, and also for the cache-only memory architectures, comma systems that we're also going to discuss. So even though we're talking about scalable ways of implementing coherence, we're going to stay in the implementation of symmetric multiprocessor SMPs, or UMA for short. And we're going to start by looking at how you can implement a more efficient snooping cache coherence protocol. So here we have a picture of a Snoopy system. The processors in this picture are at the top, connected to their caches, and all the caches are connected together, as well as to the memory controllers using some kind of Snoopy cache coherence bus. And even though this is a puny little wire in this picture, we all remember that the signals needed to implement that kind of cache coherence is maybe in the order of 400 signals, where about 300 or so of them are used to implement data broadcast on that bus. About 50 or so are implemented to implement address and command broadcast. And then we have some groups of signals that implement snoop results, arbitration, data ID, data status, and so on. The advantage, as we have seen with a Snoopy cache coherence, is that it's a very low latency. So whenever a cache sends out some kind of snooping request here, that request is rapidly seen by all the other caches, and all the other caches can take a very quick action to fulfill the coherence request of the sender. It's also fairly easy to implement stronger memory models. We've seen that the address transactions sent on the Snoopy cache coherence protocol, the order between the address transaction will define the global order between transactions in sequential consistency, as well as the store order that the total store order TSO relies on. But there are severe scalability problems with the buses the way we looked at them before. One is that each one of these wires, each one of these 400 wires here, will have many loads. So there will be many caches that will want to send and receive data from those buses, and each one of those transistors connected to the bus to send and receive will put a load on that wire, and that adds capacitance to the wire, and that's a no-no if you want to send a signal with high frequency. Another no-no is to add resistance to that wire, and resistance actually goes up since the bus wires are long. Long wires are required to connect all those snooping devices together. So capacitance and resistance, when they go up, that implies slow signal propagation. When you have slow signal propagation, that means that the bandwidth you can send using each wire goes down. How quickly you can switch between a 1 and a 0, the frequency goes down with a slow signal propagation. Still, these kind of fairly simple buses have been used even quite recently in commercial systems. So the front-side bus used by Intel up until just a few years ago to connect multiple chips together was actually a single bus, as you see on this picture, and functionality not that different from what we have seen. So how can you improve the building symmetric multiprocessors? We're going to look at 5 different tricks how you can improve the scalability without going to NUMAs and commas. One way is to implement a logic bus. So instead of having long wires that physically are shared by all the devices, we have a logic unit inside our design called the bus. And all the devices that wants to snoop on that bus have point-to-point connections to that logic unit. So here we, in this example here, we would have address transaction going both ways, point-to-point. And the data would also go point-to-point both ways here. And since we have exactly one sender and one receiver for each one of these signals, that's a point-to-point signal. And a point-to-point signal is the best kind of signal from a bandwidth point of view. One sender, one receiver. That's the lowest number of loads you can physically have on a signal. So that's good news. Higher bandwidth due to a lower resistance and lower capacitance, but you will get a higher latency for your Snoop transactions. You have to, instead of just telling everybody about your wishes right away, you now have to send it up to a specific bus unit, until the bus unit sends your transaction, and then after your transaction has been sent logically inside the bus unit, that Snoop action has to be propagated down to all the different devices. So they add at least one extra level of indirection here, which adds to the latency. Still, it's trivial to implement memory ordering, since even though we have a logic bus, you're still going to logically send one address request at a time inside this bus, and that's still going to define the order, the global memory order for SC as well as SVT. And this is a trick. So trick number 2 here is to apply this trick hierarchically. So you can have many levels of these kind of logical buses, so you don't have to connect all the devices to a single logic bus. So that means shorter wires. Shorter wires means that resistance goes down, and you can potentially run this kind of design with even higher frequency. But you also add latency for each level in the hierarchy that you add. Still, you could implement this in such a way that you do get a trivial memory ordering. You can just define that the logic bus at the top, the order at which we see transaction at that level will be the global order of our system. And we're going to look at the commercial implementation of this in just a few slides. Before we do that, we're going to look at 2 more tricks you can play to improve the Snoop bandwidth in your system. And one fairly simple trick that's been played many times in commercial systems is to add several Snoop buses. So what you can do here is to have some fairly simple convention deciding which transaction should choose each of these buses. You can just use a specific address bit and say if that address bit is odd, you're going to choose the lower bus, and if it's even, you're going to choose the higher bus. So you can stripe your transactions across these buses very, very quickly. And even though I'm showing you here sort of a physical bus that's shared here between, it's sort of two physical buses that are shared by all the devices. Of course, you can play the previous trick, and you can implement this bus using sort of a logic bus implementation instead. So you get even more scalability, even more Snoop bandwidth, twice as much Snoop bandwidth here. You can still have a trivial memory ordering model. Even though you potentially can send 2 transactions at the very same time, you can just have a convention that says of the 2 transactions sent at the very same cycle up here, by convention I'm going to define that the odd one happened before the even one. And if you just enforce that all over the system, you're going to have a defined order. The drawback is now that the Snoop devices will have to Snoop 2 buses instead of just 1, so the number of connections they need to have just doubled, and also the logic inside here, it's going to start to cost more and more. Still, we have seen over the years several commercial implementations, one by Sun and an even more scalable implementation by Cray. The Cray example actually had 4 different buses, 4 logical buses, not physical buses, that implemented this kind of coherence. The 4th way to implement a more scalable SMP implementation is to not try to push the technology for the snooping anymore, but push the technology for distributing the data. So remember that the data bus we looked at, 300 out of the 400 wires are used to transfer the data values. Now, of course, using a broadcast media to send the data values may not be the smartest thing to do, because typically you have one sender and one receiver for each data packet So you definitely don't need to broadcast the data packets to all the devices on the bus. Instead, you can use any kind of network, and you can imagine that, even though we're not going to cover networks, different networks topologies in this course, you can probably imagine that there are so many more efficient ways of implementing a network that just sends data packets from one sender to one receiver than it is to implement a broadcast bus. So you get higher bandwidth, and you potentially can use your fewer pins, because you can, with higher bandwidth, you don't need the 300 wires connected to each device anymore. They can probably do away with maybe an order of magnitude less wires, and still the system, the data bandwidth would be sufficient to match the band you would have at the snooping level. And once more, there are several commercial implementations that has leveraged this. So before we go on and look at one such commercial implementation, we're going to see what you remember so far about the properties of bus implementations to especially targeting more scalability. So I want you to read these statements, and I want you to check off all of the statements that are true, and then after you've done so, I will go through each one of them and motivate why they are true or false. So the first statement that says that having many bus loads resulting in increased resistance is not true. It's more pronounced that the capacitance goes up the more listeners you have on the wire. The wire itself, the resistance of that wire doesn't go up. So that is false. Point-to-point wires can certainly be made faster than buses. Ordered networks for data do not make it easier to implement sequential consistency. It's the ordered network for addresses that, for the snooping, that makes it easier to implement sequential consistency. The longer wire does result in a high resistance, so that is true. And signal propagation speed depends on capacitance and resistance of the wire. That one is true as well. Now we're going to look at a commercial system that plays some of these tricks to get higher kind of snooping, extending the kind of snooping that we have seen so far into at least the factor 2, 3, 4 times better than what we would have seen using physical wires. So in this system, the caches of the CPU, this is a system that's several years old, and back then they wanted to have caches of 8 megabytes, and that was too much capacity to actually be able to squeeze it onto the same die as the CPU. So these caches were implemented using external SRAM chips. Still, the snoop tags, the dual tag snooping that we discussed, the snoop tags reside on the CPU chip itself. So the CPU can actually perform snoops without consulting the fairly slow and boring off-chip SRAM. As you see here, we have a hierarchy of address repeaters. So what's going to happen when you would like to send out the snoop transaction is that transaction is going to propagate up the lowest level address repeater. You're going to send command, address, and data to that repeater. And that repeater is going to, it of course has to receive transactions from the other chips as well. And when its arbitration, internal arbitration says that now it's the time for this very transaction to be sent further, it will send the transaction to the next level. And as you see here, we have even and odd address repeaters here. So we play the even and odd trick. And when the top address repeater, its arbitration decides this is the point in time when that very transaction officially was sent, it will send that transaction to all other subsystems that it's connected to. So there are 5 other subsystems like this one. And also send one signal back, this thin red signal saying, remember that transaction you sent me with that unique identifier? Well, I told all the other subsystems that that one is happening right now. So all the address repeaters at this level get this information at the very, very same cycle. And the very next cycle, all of them will propagate that information down to the CPUs on each of the 4 CPUs in each of the 6 subsystems. So we can say a total of 24 CPUs that will get this kind of snoop address command and data happening at the very same time. What's not shown in this picture is that each of these CPUs, after they look in their snoop tags, they can propagate the snoop results back and down again using this kind of repeater structure. So after some other long fixed delay, then the snoop result of which cache believes that they are shared and which believes they are the owner, that kind of result will also synchronously arrive at all the 24 CPUs in the very same cycle. So this logically looks like the kind of coherence that we've seen before. So that snooping will decide that who should reply to this piece of data. So we're going to choose one of these CPUs or memory controllers that has the data, and then that data is going to be sent across a completely different network. We don't want to broadcast that in the same way, so we send that data through using the data tagged with the unique identifier, and the unique identifier is put together in such a way that part of the unique identifier identifies the CPU that sent out the request. So that part of the identifier will guide this packet through the hierarchy of data repeaters here, and then the unique identifier part of that CPU is tagged on, so it can tell which of its outstanding transactions just got its data returned. But once more, this does not have to be synchronously, the data packet does not have to be synchronously ordered or even seen by everybody else. It's just a point-to-point message going from this point back to the requested order here. So in this commercial system, which of these tricks did we play to make the snooping faster? So there could be one or several of these answers that's correct. And the correct answer is that we actually played all 3 of these. So we'll use multiple address buses. Well, we have multiple address buses even odd at this level over here. We didn't use an order network where we synchronously let everybody see the data appearing at the very same cycle. So we leverage an unordered data network. And we use a hierarchy or logic address repeaters here, address buses, to get the wire length down and improve the scalability